All right, we're going to be going over sections 8.5 to 8.6, and this is for Chem 1151. So as we talk about solutions, we will also want to be able to measure, we also want to be able to measure, um, how much stuff is in the solution. So a concentration basically tells us how much solute is in that amount. So how concentrated is it? And so you probably are familiar with the word concentration as in like, oh, that's very concentrated, or the opposite of like concentrated being dilute. And so different concentrations can be more dilute, less dilute, more concentrated, more concentrated or less concentrated. And we can measure the concentration in a few different ways. One way is the weight volume percent. So weight volume percent concentration, you'll see denoted as W over V. Sometimes in older text, you may also see it as M over V for mass over volume. You may see it like that. So just keep in mind that maybe if you're going through another course in the future at some point, you may see MV, which is mass volume percent. But basically, it's the grams of the solute in 100 milliliters of solution. So mass volume or weight volume, specifically 100 milliliters. And so, well, if you're given a number, it's out of 100. And so, for example, if if I told you 8.0% was your percent, then you could change this and you could say 8.0 grams of whatever my solute is equal to 100 milliliters of the whole solution. And just as a recall of what percent is, all percents are part over the whole times 100. It just so happens that the part of the solution we're interested in is the solute. So the part is the solute and the whole is the solution, right? Because the solution consists of, solution consists of the solute plus the solute plus solvent. And so the solute is usually the interesting part. The solvent can be interesting, but usually it's the solute, the thing we're trying to get dissolved. And so we can take any percent and we can turn a percent into a conversion factor pretty easily by just assuming 100 of the whole thing. That number that goes in front of the percent becomes the number that goes for the part. So if I said at 8%, let me just say 8% or 8 WV percent or percent WV, depending on, I don't know if it matters what order we put it in. We could turn that, just knowing the percentage, we can turn that into a conversion and thus use it with any sort of conversion factors. So here's an example of just some numbers. And so 5% would be 5 grams in 100 milliliters, right? Just like 8% would be 8 grams in 100 milliliters. Another type of percent we could use is volume percent. And if you are familiar with the weight volume, you could do volume, but this time we're measuring the volume of the solute, not the mass of the solute. Sometimes it's easy to measure the mass because we're talking about maybe a solid in water or a solid solute. What if we're talking about a liquid solute? Because you can have, like, for example, if you look in your cabinet, you may have isopropyl alcohol. If you look at the label on that, it'll say like 70% isopropyl alcohol. And so it's a percent concentration of isopropyl alcohol, which is exactly what this is talking about. So 70% of the thing we're looking at, 2-propanol, isopropyl alcohol, same thing, just two different names, out of 100 milliliters of the whole thing. What do you think the other 30 milliliters is? Probably water, right? And so we can just talk about it in terms of milliliters for the solute or in grams of the solute. Just make sure that you're looking at the numbers that it's asking you for. So if it asks you for WV, that's mass over volume, mass over milliliters. If you're asking for VV, it's milliliters over milliliters. So here's a problem. A saline solution using intravenous drips contains 0.92% weight volume sodium chloride in water. How many grams of sodium chloride are in 250 milliliters of the solution? And so a lot of people will just try to take 0.92% of this, which works in this case, but I could ask you a question if I gave you grams of NaCl and asked you how many milliliters of solution do we need to give this many grams of NaCl, then that wouldn't work. So let's look at it like a conversion factor so that you know it will work every time, not just sometimes. So how can I turn this into a conversion factor? I can say, go ahead and try it before you watch me. So hopefully you've tried it before you watch me do it. We can say 0.92 W, it stands for weight. So we'll say grams of the solute, which is NaCl, equals 100, so percent is always out of 100, milliliters, because it says V, that's for volume, and we always use milliliters, not liters, for the volume here of the whole solution. If I have 250 milliliters of solution, do you see how I could use a conversion to get to grams of NaCl? Pretty simple if you know dimensional analysis at this point. So here's how they're showing us they can use the conversion factor, and then they set it up for us, and we get 2 sig fig for our answer because the 250 is 2 sig figs, and then 0.92 is also 2 sig figs. So be careful with sig figs, especially in your homework. On the test, you won't have to worry too much about it, but on the homework, it definitely can be frustrating. Another way we can measure concentration is parts per million. And so parts per million is, it can be pretty simple. We're just going to take the fraction of solute to solution and times it by a million, which is 10 to the 6. That's a million. So part per million could be mass of solute over mass of solution times a million, or volume of solute over volume of solution times a million. And it's usually very small amounts. So if you have a very, very, very tiny amount of this tiny number up here versus a big number down here, we multiply it by the million to give it a number that we can work with. For example, the mass of the solute might be 10 to the negative 20 or something in 1 gram. And so 10 to the negative 20, 10 to the negative 18% is not a number that I can really wrap my brain around. But if I were to multiply by 10 to the 6, I could maybe get like a couple thousand parts per million here, and that can make sense. I know that 10 to the negative 20 is way too small, but if you have like 10 to the negative 6, for example, multiply by 10 to the positive 6, now you got 1 part per million. And so that's a more manageable number to think about versus 10 to the negative something, really, really small numbers. And then another way we can measure concentration is molarity. So molarity, of course, has moles in it. So molarity is capital M. So we got to be very careful now because we're talking about M as in meters, M as in mass as a unit, as a variable, meters as a unit. Then you've got milli, which is a prefix, and then you have mega, which is a prefix. And so this is a unit. It is not a, well, I guess it can stand it as a variable sometimes. It's actually, be careful with it because it could be both. But it is, we're going to use it as a unit, but then it means moles of the solute versus liters of the whole solution, but it's not a percent. So it's just like, weight of solute over liters or milliliters of solution, except we're talking about moles over liters. Molarity, mole liters. Here, it's not a percent. So let's think about how we could calculate this. So if I want to know the molarity, what I'm looking for is the moles of the solute and the liters of the solution. So we got to sometimes think about it in 2 different pieces. So think about if a given 20 grams of NaOH, that's sodium hydroxide, I need to find the moles of that sodium hydroxide. And then they give me 250 milliliters of solution. With that, I need to find the liters of the solution because the molarity is the moles of the sodium hydroxide per or over the liters of the solution. It's the moles of the solute, which in this case is sodium hydroxide, over the liters of the whole solution. So how can I go from grams to moles? Well, if you haven't stopped and tried it yet haven't stopped and tried it yet, go ahead and try it now. Okay, so hopefully you've tried it. We can use molar mass to take us from grams to moles. Where do we get this number 40 from? Well, we look at the periodic table, add up a sodium, add up an oxygen, add up hydrogen, you get around 40 here. Take our grams and divide by our molar mass to cancel out grams and get moles. So that'll give us the first part. And then we need to do the liters. And so you can use whatever conversion we have for milli to get liters. And then we'll do the last part, which is combine them. Moles divided by liters gives me the molarity. The unit is the same as, this is kind of, you can think about it as like a variable, but the unit is actually the same thing. So capital M is our unit here for molarity. So molarity is also a conversion factor. It's moles per liter. And so we can think about it algebraically. And of course, you know what I'm going to say to that is that if you want to do it algebraically, you can, but it's probably better for you just to think about it and as a conversion factor. So moles per liter. So if I give you the molarity and I ask you for volume in milliliters and I give you moles, think about how we can use the molarity as a conversion factor. So molarity, we can really think about it as mole per liter. And if we have that per, we can rewrite it as equals 1, remember? So 0.30 mole per liter turns into 0.30 mole per turns into equals 1 liter. So now I have a conversion factor. And this is a lot better for most people than trying to do it algebraically. You can also try to solve this algebraically, but keep in mind that when you do it algebraically, you're going to get out liters, and it's asking you for milliliters. And so, or what if it gives you grams instead of moles? And you have to do the algebra, but then you also have to do conversions outside of the algebra. So just make sure that you're keeping track of your units and what you're doing. If you seem to start to have trouble with it, then try using it as a conversion factor instead of using it algebraically. But go ahead and give this a try. See, can you go from moles to milliliters is what it's asking for. It says it's asking for liters here, but we're really asking for milliliters. So they actually get the liters first and then go to milliliters. But if you're doing it my way, we'll just do it all at once. And so I'll show you, this is just showing you algebraically kind of how they rearrange the variables and then they solved. Here's how I would do it. I would say 0.025 moles, and then I would use my molarity, which is 0.30 moles on the bottom, 1 liter on the top. And then I would say 1 liter, 1,000 milliliters. Instead of doing it in so many steps, I would just do it all in one. Save myself a lot of time and effort, I think, and thinking. I think that it's easier. You don't really have to think about what you're doing algebraically. You just need to be able to figure out what units you need to cancel, right? And if you're good at dimensional analysis, you should find that it's a lot less taxing than algebra, maybe. So 83 milliliters is what we'll get either way. It's up to you how you want to do this. If you want to break it into sections, if you want to do it algebraically, that's fine. But I think that it's probably worth looking into if you're struggling with it to do it as a conversion factor. That's all for this video. Let me know if you have any questions.